Section: Introduction. In this section, we discuss the current challenges faced by vision language models, VLMs, that are trained using web datasets. These datasets often rely on alt text descriptions associated with images, which can be ambiguous and limit the model's capabilities. To address this issue, recent efforts have focused on creating high-quality image text data through human-written or model-generated caption datasets. However, both approaches have their limitations, such as subjective outputs from human annotators or incomplete descriptions from models. To overcome these challenges, we introduce ImageInWords, IIW, a framework that combines human annotators' quality with machine-generated metadata to curate detailed and accurate image descriptions. The process begins with object detectors identifying objects in an image, followed by a VLM generating captions for each object. These initial captions may contain errors or lack detail, which are then refined by crowd workers to create more comprehensive descriptions. This iterative process continues at both object and image levels to ensure detailed and accurate annotations. The resulting IIW dataset consists of 9,018 images, each with a hyper-detailed description containing an average of 9.8 sentences and various parts of speech. Human evaluations show that our descriptions outperform those from other datasets in terms of comprehensiveness, specificity, and human likeness. Additionally, we fine-tune a model using the IIW dataset and demonstrate its superiority in generating detailed descriptions compared to other fine-tuning sets. Furthermore, our model-generated descriptions are preferred by evaluators, considered closer to the original images, and exhibit higher reasoning accuracy in compositionality benchmarks. Overall, our framework produces high-quality image description data that can benefit various applications in VL research, including text-to-image models and assisting individuals with visual impairments. Section Summary. In this section, we introduce the challenges with current vision language models, VLMs, trained on web datasets using alt text captions, which often lack content specificity. To address this, we present ImageInWords, IIW, a framework combining human annotators and machine-generated metadata to curate detailed and accurate image descriptions. Our resulting IIW dataset outperforms existing datasets in terms of description quality and is shown to enhance model fine-tuning, leading to improved image description generation and compositional reasoning accuracy. Section: Related work. In this section, we have explored the existing research on image captioning, which has evolved from CNN and LSTM models to transformer-based VLMs. These models have been evaluated on challenging datasets like VizWiz and NoCaps, containing captions with an average of 15 words or fewer. While there are datasets with dense image descriptions, such as Pixlore and DAC, they still face challenges like introducing hallucinations and biases. Our approach, called DOCCI, aims to improve image descriptions by combining VLM-generated outputs with human annotations. Unlike other methods like DCI, which use human annotators to create denser descriptions, we seed our annotation process with VLM outputs and allow crowd workers to refine the information iteratively. This sequential refinement process results in detailed and coherent image descriptions, surpassing the quality of existing methods. The IIW dataset, consisting of 9,018 images, was annotated by human annotators following detailed guidelines. These guidelines emphasize providing detailed and coherent descriptions, starting with a concise summary and describing objects in order of saliency. Attributes like function, shape, color, and relationships with other objects are highlighted to ensure rich image descriptions. Our annotation methodology involves seeding the process with VLM outputs to expedite human annotations and employing a sequential augmentation approach. This sequential process improves efficiency and quality by building upon previous annotations, leading to a single comprehensive output per image. The iterative nature of our framework enhances inter-annotator agreement and individual quality, showcasing a significant improvement in image description quality. Section Summary. Related work image captioning has evolved from CNN and LSTM models to transformer-based VLMs, with datasets like VizWiz and NoCaps. Pixlore and DAC propose methods to generate detailed captions using vision language datasets and VLMs, aiming to improve compositional reasoning. While model-only approaches are cost-effective, combining VLM outputs with human annotations, as done in DCI and IIW, results in more detailed and accurate image descriptions. Section: Annotation Framework. In this section, we present the IIW annotation framework that we developed based on specific guidelines and methodologies. Our framework is designed to annotate images for two main tasks. These tasks are carried out sequentially, starting from either VLMs or existing human annotations. Each task may involve multiple rounds of annotations, with each round building upon the previous one. Examples of annotations and screenshots of the user interface can be found in the supplementary materials. For Annotation Task 1, we focus on capturing detailed information about objects and their attributes. Similar to the visual genome dataset, we aim to annotate each salient object in an image with a triplet consisting of a label, a bounding box, and an object description. The label for an object can be any word without restrictions, and the description should focus on the object while considering the overall context of the image. The bounding box indicates the location of the object in the image. To start the annotation process, we initially use an internal object detection model to generate a list of object labels and bounding boxes. Object descriptions are then created by cropping the image to the object's bounding box and generating a caption using a Poly 35B model that is periodically fine-tuned. Our approach is flexible and can work with various VLMs, object detection models, or image segmentation techniques. Annotators are tasked with refining the list of objects by editing, removing, adding, or merging annotations based on accuracy, importance, and relevance to the overall image. They are also encouraged to update labels to make them more precise. The final output includes a list of objects with their labels, bounding boxes, and descriptions, focusing on individual objects to ensure comprehensive detail capture. All annotations follow the guidelines provided. For Annotation Task 2, our goal is to create a detailed description of the entire image. Building on the data from Task 1, along with optional domain-specific metadata and a VLM-generated image caption, annotators work to compose a comprehensive description of the image. The primary responsibility lies with the first annotator, and subsequent rounds of annotation aim to refine and enhance the description. By involving multiple annotators in sequential rounds, we aim to improve the quality of the output and reduce subjectivity. Annotators are encouraged to focus on enhancing the description and only remove information if it is clearly incorrect. They have the freedom to rephrase existing information to add new details. We conducted experiments with 3 sequential annotation rounds and monitored the similarity between outputs using n-gram-Jaccard similarity. Once a high level of consistency was achieved, we reduced the number of rounds. Our experiments showed that a high level of similarity can often be reached between the first 2 rounds, indicating high quality from individual annotators. In our evaluation experiments, we assessed the quality of the IIW dataset and its usefulness for fine-tuning. We started with text-based automatic readability metrics and proceeded to human evaluations to compare our annotations with prior work. We fine-tuned Poly 35B models on different datasets and compared the outputs to evaluate the effectiveness of our approach. We also conducted downstream evaluations to assess the richness of the model outputs and their impact on tasks like text-to-image generation and vision language reasoning. Section Summary. In this section, we introduce the IIW annotation framework designed to annotate images in 2 tasks. The first task focuses on fine-grained objects and attributes, capturing a triplet of label, bounding box, object description, per salient image object. The second task involves formulating a detailed overall image description using seeded data from the first task and additional domain-specific metadata, refined through sequential rounds of annotation to enhance output quality. Section: Automatic readability measurements. In this section, we use a set of readability metrics to compare the writing styles of DCI, DOCCI, and IIW before assessing them against human descriptions. These metrics estimate the level of education needed to understand a text, using units like education years or grade levels. By analyzing these metrics, we can see that IIW generally has a more mature and articulate writing style compared to the other styles. We have developed a human evaluation framework called Side-by-Side, SXS, to assess descriptions based on 5 metrics: comprehensiveness, specificity, hallucinations, quality of the first few lines as a TLDR, too long didn't read, and human likeness. The evaluation is done on a 5-point scale, with higher numbers indicating better quality. This framework is used to compare human-authored IIW descriptions and fine-tuned model evaluations. To evaluate the quality of human-authored descriptions, we annotated images from the DCI and DOCCI test sets using the IIW framework. The results show that IIW descriptions outperform DCI and DOCCI in terms of comprehensiveness, specificity, hallucinations, TLDR quality, and human likeness. This indicates that IIW descriptions are significantly better than those from previous works. When comparing IIW human annotations with outputs from the GPT-4V model, we observe improvements in comprehensiveness, specificity, hallucination, TLDR, and human likeness. While GPT-4V performs better than human-authored data from DCI and DOCCI, it still falls short of reaching the quality of IIW human-authored descriptions. After evaluating IIW human annotations, we analyze the impact of fine-tuning with IIW data versus prior annotations. The fine-tuned models show better performance in replicating their own style. When comparing the fine-tuned models on out-of-distribution images, IIW models exhibit improvements in comprehensiveness, specificity, TLDR, and human likeness compared to DCI and DOCCI. Overall, IIW model-generated outputs are preferred by human judges by an average of 31%. The IIW Poly 5B fine-tuned model shows potential for improvement compared to GPT-4V, particularly excelling in human likeness and understanding the TLDR concept. Section Summary. In this section, we utilize automatic readability measurements to assess writing style differences between DCI, DOCCI, and IIW before comparing descriptions with human side-by-side, SXS, evaluations. By running readability metrics on both human-authored and model-generated descriptions, we observe that IIW exhibits a more mature and articulate writing style compared to the other alternatives. Through our human SXS framework, we evaluate the quality of human-authored IIW annotations against DCI and DOCCI, finding significant improvements in comprehensiveness, specificity, TLDR quality, and human likeness, indicating the superiority of IIW descriptions over prior works. Section: Reconstructing images with IIW descriptions. In this section, we explore how model-generated descriptions from the IIW framework can benefit various downstream tasks. We start by investigating how IIW descriptions can enhance the accuracy of image reconstructions by T2I models. We use fine-tuned VLMs to generate descriptions for 240 images and feed these descriptions as cumulative inputs to an Imagine model variant. By breaking down the descriptions into sentences, we aim to compare the quality of IIW descriptions with previous methods. We evaluate the generated images through human ranking and clip similarity scores, showing that IIW descriptions consistently lead to better image reconstructions, regardless of the input unit length. Next, we delve into compositional reasoning using IIW descriptions. We modify image captions in datasets like Arrow, SVO probes, and Winnoground to test different types of vision language reasoning. We assess if IIW descriptions can help distinguish between real and incorrect captions in these datasets using an LLM-only setup. Our results demonstrate that incorporating IIW descriptions significantly improves task performance, with accuracy gains in various reasoning tests. The IIW fine-tuned model outperforms other models in Aero Visual Genome Attribution and Relation, VGA, VGR, and Winnow-ground tasks. Furthermore, we release a subset of human and model annotated IIW image descriptions, along with human SXS results, to encourage the development of new evaluation metrics for automated detection of anomalies in generated descriptions. This dataset aims to facilitate fair comparisons across different methods in future research.